Welcome. In the previous video we started to look into a simulation where we have now adapted the model a little bit step by step to make it more realistic. And we assigned some parameters, especially for the meteorological conditions, radiation, and we also made a test of using this input file for the meteorological data that is actually using two different sources, one from the local meteorological station at the field and one from the synoptic station, as has been processed by those OpenMe2 algorithms. Now I would like to continue a little bit where we finished, because we finished by making a multi-run. A multi-run is a run where we allow many things to change in a sequence to investigate not only one change but many changes at the same time. So it is sometimes a little bit complicated, but it is the most powerful method we have to try to understand the behavior of the model. And I will this session look a little bit more into that. First of all, we can say that when we are running a multi-run, then we get one additional file called mbin, multi-binary. This is a binary file that cannot be understood by anything else than a model. The normal file name for the XML file is shifting in the naming from a Pete inversion with a number to Pete inversion multi and the same number. In addition, we have a directory created called Pete inversion, the same as the start of the file name, and that particular directory includes a number of also binary files. So one multi-cup, one V1 and one V1 residuals. All those are a little bit tricky. The two first are PDF files, so they can be understood by, just clicking on them. You can get some information, but here we could not even open this because this file did not contain anything sensitive. So it is a little bit more mysterious to look into a multi-run. But we have many tools and we have many methods to examine a multi-run, and that's what we should start with here. First, I open the multi-run by clicking on this XML file. And then it explains that it is a completed multi-run, and these 11 runs have been done. And the 11 runs have been done with parameters that we can find in the multi-run tab. So in the multi-run we have now two parameters. They are both in dimension number 1, and the first is this sequence number met file. If I click on that, we will see that it's jumping up and down. We were shifting between station number 1 and station number 2 just to see what type of impact it might have. But we also take one more parameter, and that was the drain level with the stochastic behavior. So that parameter is randomly between -1 and 0.2 meter, and then we can see to what extent that will have an impact on our outcome. So that's what we have done with the input. The parameters have a number of possible changes, and then we could look to the results, and if we click to the validation, we can say this validation sheet looks a little bit more with more information compared to before. We have all the different validation variables. Actually, we have 15. We have 2 groundwater levels. We have 6 measured water contents or measured soil temperatures for each of the 2 location number 3 and location number 4. And then by accident we had one water content that was not connected to a theta sensor, it was connected to a specific layer. If we now would like to see the performance of the model, we could first of all click any one of those here where we have various performance indicator, and you recognize first of all R square, that is maybe the most well known, and then we could see that this R square is different for each of the different runs. So this means that it is sensitive to the parameters. The same is, for instance, if I look to another, like the mean error, it goes also up and down. And we have root mean square error, and we have log likelihood, and we have a Nass-Sutcliffe's R2. I don't know to what extent you are familiar with those indicators, but they are, like many other things, partly similar, partly different, and people have their preferences which one they would like to use to select one run from another. Okay, so this is of course something that we could look to a lot, because there are many variables, many performance indicators, and there are also not only the indicators, one for each run, but we can also, for instance, make an ensemble. If I right click here, I can estimate a mean value for the ensemble of the time series. And if we click one of those, for instance here, the soil moisture, then we will see a type of band, not a single run, but instead the variability that is caused by those parameters that we have used in the multi-run. So it can be many various ways to just play with what we have produced here. But first of all, we have to admit that if we now compare, for instance, our theta sensor with the measured, they differ a lot. This is much lower, this is much higher. So that's obvious that we have much more of, and this was if we looked only the measured. So the nice thing is that we could look to time series, and we could look to performance indicators, and we could make various type of more direct graphical evaluation by just looking. We don't need to look to the specific values of the statistics. We can also look to the values how they are just shown when we look to graphics. But before we look to more, I would like to say that this is not a good result. You know, if I look to this now, for instance, mean error of the soil moisture, it is for all of the runs 15% more than what we have simulated. Here it's even more. It's up to 20% more than what we simulated. And the R squared was very low. So this is not something that we could be happy for. The best we could find here was for the soil temperatures. And then when I click this, you directly see a pattern, and you could directly understand that these patterns that you have here, that's the pattern when we are jumping between the two stations. So one of the stations have a higher performance and the other have a lower. But still, I mean, now it's relatively high R square for a temperature, but also for the temperature it is not good when we look to the mean value. It is substantially away from zero. It is -4 degrees too cold. So I would like to redesign this and then get something that is more sensitive for a more complete analysis. And to do so, we always create a new document for making it something that includes the modifications. And we can start to go to the multiruns, and then we see that this is what we had seen before. The drain level and the sequence number for selecting of the climate file. Now I feel that we should take some more parameters. And first of all, it looks like the soil is not a very good representation. So we look to how the water retention curve looks like here in the model by right click, and then I see that this is a clay soil, substantially heavy clay soil with a relatively high saturation value, a wilting point that is high, and a lambda that is low according to those Brooks Gray. In my understanding, we have a sand above the peat and not the clay above the peat. So we could try to make this to be a sand, and then we just put lower values to various parameters. And what I will do here is actually that I will take the default values of the model that is a sand. So wilting point 4 and residual we have 1, and then this there's upper boundary. I can explain that maybe later what it is, but now we have the default sandy soil in the model, and maybe we can take one of those parameters for a multi-run selection. So for the air entry, for instance, I can set that as a multi-run. And now I also would like to do it, I could put it into dimension 2. But I would like to create a new dimension. So now we have not only dimension 1, we have also dimension 2. And then I put this air entry in this dimension 2, and I can select a value from, for instance, 1 to, it suggests a range here that is very wide, but we can take a range from 1 to 10. And then we say OK. And now this is a range from 1 to 10 in the dimension number 2. And going then to the Multirun tab, we can see that this is now our parameter number 3 in this. Another thing that I also would like to do is to say that to put this sequence number in a table randomly jumping up and down may not be so clever, but we can put it in a separate dimension. So we move this drain level to dimension 2 and keep this sequence number in dimension n, but then we reduce the number. Since we have only 2 different choices, we take the 2, and then if we right click and show this here, it is going from 1 to 2. And then in the other dimension we have drain level and air entry that have a stochastic variability, and they are taking 11 values. That's 2 times 11 makes 22. That's not enough for making a more serious evaluation of the model. So I would suggest at least to take 100 to make it a little bit more realistic. And of course we could have continued now to select more and more parameters, but as a starting point we could be happy with those 2. Actually it is only the drain level and the type of, we can call it pore size distribution, showing to what extent we have a high air entry or not. That is a very important property. Okay, we make a Multirun then, and we do it the same way as we have done, and now it will take a little bit of time, and you could see here that it is counting the number of runs, and now 200 runs have been done, so it's relatively quick when we have such a short period of time. And then we should be able to go back and look to the same information now with the Multirun with 200s. And we can see that if I look to the sequence number, again it's jumping up and down, but the drain level, that is now arbitrarily for those 200, but it is like pairs, so it's keeping 2 values when the sequence number, so they are not randomly in that respect, so it's only making it like 2 loops. One loop goes fast and the other goes later on. So we have now a more interesting testing of the model with different drain levels and different air entry values, and it will be nice to see what type of impact it have. And then we revisit the same validation tab, and we can, for instance, look to the R² value of the theta sensor at 30 centimeter. And then we see that now it's much better. It is from 0.1 up to 0.4 at least, 5, yeah, not too bad. And if we look to the mean error, it is to some extent beneath 0, to some extent above. This is a very good sign in my view. We should always be, around 0 when we are making a calibration. If I look to the theta sensor in the top, they are all overestimation, but still not that big as we had before. So it looks like we have made a type of progress. We can also look to the temperature, and then we look to the temperature at first 30 centimeter, and then we see that we are still minus 3 degrees. So we have much colder in the model than what we have in the real world. And I think it's the same. Yeah, it's the same when I look to the other horizons. So we have fixed soil moisture to be around 0, but temperatures are still far away from 0. But on the other hand, the temperatures have nice performance. They have now R² of up to 0.92, and if we want, we can look to the ensembles of those. First, I right-click and estimate the mean value, and then we could look to the temperature ensemble, and then you see the ensemble of the temperatures, and we could compare that with what we have measured. And then we notice that here it is approximately 4 degrees below all the time. So it's a systematic error, but the dynamics is not too bad. So that's a good sign. I can look to this a little bit deeper, and it's the same. Okay, so we should try to find explanation why the temperature is systematically much lower in the simulation than what we have in the measured. There can be many reasons, and we haven't looked to any of those parameters for the temperatures, but most important is to go back to the switches, and then I look to the switches, and I will look to the switches for the now soil frost and soil heat. And then we can say, first of all, we have an initial heat conditions that is an assumed uniform temperature. So the temperature in the start is probably too low in the simulation, since it was wrong from the very beginning. So maybe that could help. And then I switch from the switches to the parameters, and now I see those parameters that we have changed compared to the default, but there's nothing in the soil heat, so I clicked on the plus to see those, and then we come to the section of soil heat flows, and where we have a parameter called soil init temp constant 10 degrees at the 1st of September uniformly. I think this is a good candidate for maybe putting into the calibration or just change it to get something where we don't need to have a systematic error with respect to the temperature level. So we have a good candidate for a modification, and to use that we again need to make a copy, and we need to go into this group with the soil heat, and then we find the parameter, and then we can maybe say that it should be maybe 4 degrees above. Maybe we put it to the multiruns, and maybe we can say that it could be from 12 to 16, and we put that into dimension number 2, and we click on that. So now we have first of all changed the level, and then we are allowing also a range of that as an uncertainty. Okay, so we will make this once again, go to the run info and click make multiple runs. And we wait for the results, and it will take not too long time, but now it's ready. And now we can first of all look to the mean value of the temperatures. So I look to the same temperature at 30 centimeter, and then I see that okay, it helped. We are coming higher, and we are getting a variability, but we are still far away. Also here in the more surface layer. So something is wrong with the temperature with respect to level, but not with respect to the dynamics. The dynamics is relatively well defined. We may say that this is good enough for also trying to find a type of selection, not looking to the full ensemble of all the runs, but looking to a sub-ensemble that is a type of posterior ensemble compared to the prior ensemble that consists of all those 200. I only would like to introduce this because this is a new window, and it's called Eval Coffee Multi. And you see this also when we look to the view, that it is in the docking station, and I have it now together with my sim and PD file. I will go more in detail on this, but this is not only showing the values, it also gives you the chance to make selection. So you could take a sub-selection based on any of those variables and based on any of those performance indicators. So if you feel that you would like to have an R-square that is the highest, and you can go to one particular variable that you have high priority for, like for instance the soil temperature at 7 centimeter depth. Then you follow that until you come to this limits for selection. And then if you right click, you could say that you could do a new selection, not the 200, but you could keep only the 10 best. And then it gives you values of what are the R-square that corresponds to the 10 best. And if we now go into our simulation sheet and go back to this sim validation, and then I right click for estimating a mean value, and then we look to this temperature sensors. Then we get something that is much sharper, much smaller band, because this is now just those that are the best, and we could compare that with again the type of results we have from the measurements. So maybe you feel that this is still a disappointment. We are sharp with respect to the size of the band, but we are still systematically much below. Okay, how comes? We could explore the model in that, and we could also see how does now our parameters corresponds to those runs that belongs to this ensemble compared to those that we had prior we make any selection. To look to the parameters in the graphic way, I visit Multirun tab, and then I can see that here we have posterior values of those parameters. So they have a new posterior mean that differs from the prior mean. So for instance, the air entry have been going from 5.5 to 3.4, and soil init temperatures are taking the value of 12. Actually, it was not taking the highest value, it was taking the value of 12. 14 and 16 maybe should have been better for the mean value, but for the dynamics 12 was still the best. So to select based on the R-square has a disadvantage of being mostly emphasizing the dynamics and not thinking about the level or the bias with respect to the mean value. So we can go back to this evaluation coefficient, and then we could say that we was not so happy with looking to the 10 best with respect to R-square. And then I can redo this, and I can first reset, so I have all runs, and then we could try another indicator. And for instance, we can take the mean error, and then we see that the mean error is here given. It's a little bit hard to read, but you could say the best we could get here are actually for something that is an underestimation by approximately 2 degrees. So we can say we exclude all those that have the... Now, if we could sometimes just ask for for instance, 10 best, but we could also put values here after unlocking, because we have to unlock it to make clear that we could modify those values. But now it might be tricky to see exactly, because it's a little bit small, but I will make one try just to put it to from -2 up to -1.85, and then I right click and then I update the list of accepted runs, and then I find 20 that satisfy those conditions by the specific values that I have selected. Okay, now we could go back to the sim, and we could for instance first, okay, now I come to the parameters, and then we see that now the parameter is 15.74 for this initial temperature. So now we take the highest of those. And if we look to the dynamics that will be in the validation, we have to now clear the previous, and then we should estimate a new mean value, and we look to a new temperature, and then we get a comparison. Okay. Oh, no, it's great. Now it is more or less the same level in the beginning, but sorry, it's still substantially wrong in the end. So the initial values help here, but there's no help of the initial values in this later part. So more thinking on why, more way to understand how we could get also the temperature to be good in the long run. So this evaluation is, in my view, quite funny, but it's also partly an endless process. I look here to the soil moisture, jordfukt at 3 centimeters, and then we see this is the performance we get with respect to the soil moisture when we put the requirement on the soil temperature. So here you see that it's quite a wide range, and if we had put the criteria on the soil moisture, then that range should have been decreased, and probably we should have been able to get also the dynamics much more precise. So I think now you should have the chance to start think by yourself, and you should be able to think based on, first of all, your conceptual understanding. Here we have the saturation level, also very wide range. So we have simulated everything in this range. And one of the measurements is here, and the other that we had from location 3 was up here. Oh. So we can improve in one part, but we can also be totally wrong in another. And especially if we try to compare the model with two locations, it can never be good for both locations. It have to be good for one of the two. So to continue, we can of course start to look to both the conceptual scientific understanding of the system and learn more about the, of course, soil physics, but also the energy balance and the hydrology. I would like to continue in the next to see if we can also be closer and we could see how far should we go by this calibration. Because of course we can use the model as a pure model for just getting a type of performance without bother so much about exactly what are the physics and what are the phenomena that are represented in the model. So some people, especially those that are in my generation, they thought that this was more or less what people can say bullshit. You know, you should not just take something and try a ladder and see what happens. You should have a careful examination on understanding what you could measure and how you could explain and how we could look to that together with some of the performance indicator. But that will be for the next. Thanks for viewing this. Bye bye.